Jnanam paramam dheyam. Knowledge is supreme.
Today I am going to start with heterogeneous reactor analysis. So, we will start with looking at heterogeneous reactor data and the reactor design. Okay. So, we will look at the heterogeneous analysis for reactor design. So, the general algorithm for designing a reactor is as follows. So, the first step is to deduce a rate law, The second step is to find the mechanism behind the reaction, and the third is to find the rate parameters, and the fourth step is to design a reactor using all the information that has been found from the previous three steps. So, that is what we are going to start today. So, today we are going to look at the rate law and we are going to look at the mechanism and how to estimate rate parameters, and then we will go march forward to the design of the reactor. So, as an example, let us take the hydro-demethylation of toluene, whose reaction essentially follows this scheme: C6H5CH3, which hereafter I will call as T. T stands for toluene, and plus hydrogen, which will hereafter be called as H, leads to benzene, which will be henceforth called as B, and methane, which will be henceforth called as M. Okay. So, the objective is to design a packed bed reactor, which will be henceforth referred to as PBR, and in order to do this we need to find a rate law, that is, we need to find the rate of generation of toluene per unit gram of catalyst or per weight of the catalyst that is used in the packed bed reactor. Okay. So, in order to achieve this objective, let us start with the experimental data. So, there has been experiments that have been performed under different conditions and different partial pressures of these different species, toluene, hydrogen, methane and benzene, and different combinations. Various experiments have been performed and the rate in terms of gram mole of toluene per gram catalyst per unit time have been measured. So, there is 16 experiments and you could actually classify them into 4 different sets. The first one and the second one by changing the partial pressure of methane, and then the second one by changing the partial pressure of benzene, and then the third set by varying the partial pressure of hydrogen, and the fourth set by varying the partial pressures of toluene. Now, remember that partial pressure is a reflection of the mole fraction of each of these species. So, we can now deduce a rate law by looking at this experimental data. And so, as a first step, let us try to see how the rate law depends on. So, dependence on, let us say, methane. Okay. So, let us look at the dependence of methane, the concentration of methane on the rate of the reaction. Okay. So, if we look at the data here, so if you look at the first 2 data sets, we will see that as the partial pressure of methane is increased by 5 times, one can observe clearly from the data that the rate is hardly changing, which means that the methane has little or almost no effect on the rate of the reaction. Okay. So, clearly we can observe that the methane M is weakly adsorbed or goes directly into the gas stream. Into the gas phase. So that is an important reduction. So, which means that methane is hardly contributing to the rate of the reaction. Methane does not affect the rate of the reaction. Okay. So, that is an important reduction that one can observe from the experimental data. So, next let us look at what is the dependence of benzene on the reaction rate. If you look at the second set, that is runs 3, 4, 5 and 6, and you can see that there is a significant effect of benzene on the reaction rate, particularly if the partial pressure of benzene is increased, then there is a decrease in the reaction rate, overall reaction rate. So, which suggests that the concentration of the benzene has to appear in the denominator of the reaction rate. So, which means that, so if I look at the dependence, so runs 3 and 4, they suggest that the rate decreases with increase in the benzene concentration or the partial pressure. Okay. So, this suggests that the reaction rate must somehow be proportional to the partial pressure of benzene which appears in the denominator of the rate law. This is because the rate now decreases with increase in the concentration of the benzene, that is the partial pressure of benzene. So, therefore, the rate of generation of toluene, which is R T prime, which now is given by 1 by, it should be approximately be proportional to 1 by 1 plus Kb into Pb plus other components, where Kb is basically the corresponding equilibrium constant. So, next if we look at the data set again, and we want to know what is the dependence of toluene on the reaction rate. So, let us look at the data set 10 and 11 excuse me, and it suggests that 10, 11 and 12 suggests that as the toluene partial pressure is increased, there is an increase in the overall reaction rate, which means that at lower concentration of toluene, there is an increase in the reaction rate. However, if we go to a much higher concentration of toluene, for example, look at the run 13, 14 and 15, that a significant increase in the concentration of toluene does not have any effect or marginal, that has only marginal effect on the reaction rate. Therefore, this suggests that the dependence of toluene must appear both in the numerator and the denominator of the reaction rate. So, let us summarize this here. So, dependence of T, so runs 10 and 11, it suggests that at low concentrations, at low concentration of toluene, the rate increases with increase in concentration of T. And similarly, runs 14 and 15, it suggests that at high concentrations of T, rate remains constant, is almost constant. Okay. So, that is the reduction that we can get from the experimental data on the dependence of toluene, concentration of toluene on the reaction rate. Okay. So, the only other component which is left is basically the hydrogen, and so let us look at the experimental data again. So, the partial pressure of hydrogen, if it is increased by twofold 1, 2 and 3, it appears that there is a linear increase in the reaction rate, which means that when the partial pressure goes from 1 to 2, the reaction rate is almost double, and from 2 to 3 it is almost double of that. So, this suggests that the reaction rate perhaps depends linearly on the concentration of hydrogen. Okay. So, if we look at the dependence of hydrogen on the reaction rate, so we run 7 and 8 and 9 suggests that the rate increases linearly with the concentration of hydrogen. Okay. So, this means that the hydrogen is perhaps either not adsorbed on the surface, or it is immediately goes into the, it is not adsorbed on the surface, or the surface coverage of hydrogen on the catalyst site is insignificant. Okay. So, therefore, now we can combine all of these different different observations from experimental data. So, combining the observations, one can deduce that the reaction rate perhaps must have a form which looks like this. So, it has to depend linearly on the concentration or partial pressures of hydrogen, and it has to depend, it has to increase with the concentration of toluene when the concentration is lower. However, it has to remain constant when the concentration of toluene is larger. So, therefore, it has to appear both in the numerator and the denominator, and similarly the benzene has a reverse effect. Benzene, as the concentration of benzene increases, the rate decreases, and therefore, it has to appear in the denominator. Okay. So, now we can convert this proportionality into an equivalence by putting a rate constant in front. Okay. So, if I stare at this equation, you can see that the rate now is directly proportional to the partial pressure of hydrogen, and it appears both in the numerator and the denominator of the reaction rate with respect to the partial pressure of toluene, and then it appears in the partial pressure of benzene appears in the denominator of the rate expression. Okay. So, this actually provides a method by which one could actually deduce what is the possible reaction rate law based on the experimental observations. This data is only an example, and in general data may not be available in such a form, and it may not always be possible to deduce rate law by inspection. So, the next step towards finding the rate law, if we go back to the set of different steps which is involved. So, we have now found the rate law. So, we need to next go ahead and find the mechanism that governs this particular set of heterogeneous reaction. So, the next step is towards finding a mechanism. The next step is finding a mechanism. So, now we have to make certain assumptions here. So, if we assume that the toluene is adsorbed on the surface, so remember that from the experimental data we observed that at low concentrations of toluene, the reaction rate actually increases with the partial pressure of toluene. However, at high concentrations or high partial pressures of toluene, the reaction rate almost remains constant, which suggests that the toluene must actually be adsorbed onto the surface. And so, based on that observation, we will make an assumption that the toluene actually is adsorbed on the surface of the catalyst at which the reaction is occurring. Okay. Then, the second important assumption we will make is that the toluene which is adsorbed on the surface, it reacts with the hydrogen which is present, and when it reacts with the hydrogen which is present, because the partial pressure of hydrogen affects linearly the reaction rate, we will assume that the reaction actually occurs between the toluene which is adsorbed on the surface and the hydrogen which is present in the gas phase. Now, after the reaction is completed, the products which are formed are basically benzene and methane. Now, we observe that the methane hardly has any effect on the reaction rate, which perhaps suggests that the methane must actually directly or immediately go into the gas phase, and benzene must, it affects as the partial pressure of the benzene increases, we can see that there is a reduction in the reaction rate, which suggests that the benzene actually has to stay adsorbed on the surface and then later get released into the gas phase as a product. Okay. So this can be captured in this statement here. So the reaction, the toluene which is absorbed reacts with hydrogen in gas phase, and it leads to the production of benzene which remains adsorbed on the surface, and methane which goes into the gas phase. Okay. Then as a third assumption, after the benzene gets adsorbed on the surface, the product has to come out of the reactor. So, therefore, the benzene actually gets desorbed from the surface and then it goes into the gas phase and then leaves the reactor. So, this can be stated as benzene is desorbed from gas phase, and then so you must have learnt in the previous lectures that there has to be a rate limiting step. So, we will assume that the heterogeneous reaction is actually a surface reaction limited step, and this is in fact not a bad assumption, because 75% of the heterogeneous reactions are actually limited by the surface reaction. So, therefore, let us assume that it is a surface reaction limited, it is surface reaction limited. So, let us take each of these steps one by one and then try to write a simple rate law for each of these steps. And so, there are three key steps which we have actually deducted from the experimental data and the form of the rate law. So, the first one is the adsorption. So, this is the toluene which gets adsorbed onto the catalyst surface, and so this can be captured by the following reaction. This can be depicted by the following reaction. So, it is the toluene in the gas phase which actually goes and occupies a vacant site S. S represents the catalyst site at which the toluene gets adsorbed, and that leads to the formation of this complex, which is basically the toluene and the site, which is basically means that the toluene is now attached or resides on the location of the catalyst site. Okay. So, we can now also represent saying that there is a specific constant which corresponds to the formation of or adsorption of toluene on the catalyst site, and also it is an equilibrium process, and so therefore, there can also be a simultaneous desorption. So, if Ka corresponds to the specific constant which captures the adsorption of toluene onto the site, and K minus A corresponds to the desorption of the toluene from the catalyst site into the gas stream. Okay. And then the second step is the reaction. So, the hydrogen which is present in the gas phase, that now reacts with toluene which is residing on the catalyst site to give the products, where this will be benzene which is adsorbed, which continues to be adsorbed on the surface, plus methane which goes into the gas phase. So, this is the second step where hydrogen in the gas phase reacts with the toluene which is now adsorbed onto the surface of the catalyst site, and that leads to the product formation, where the benzene, which is one of the product, it remains adsorbed on the catalyst site, and then methane is formed along with it, which immediately goes into the gas phase. And the reaction rate corresponding to that can actually be here it is depicted as Ks and K minus S for forward and the backward reaction. The third step is the desorption of benzene. Third step is the desorption of benzene, where the benzene which is adsorbed onto the surface of the catalyst is now desorbed into the gas phase, where benzene goes into the gas phase and leaves the catalyst site is emptied. Okay. And so, this reaction, the specific constants can be represented as Kb and K minus B. Okay. So, these are the three steps that we have identified based on the experimental data and also based on the some of these observations that we got from the experimental data. Okay. So, now what we are going to do is we are going to take each of these steps, each of these individual steps, and then try to find out what is the reaction rate law, and then we are going to, we have identified what is the we have assumed what is the limiting step in each of these three, which one of these three is a limiting step, and then based on that we are now going to find out a rate law for this particular heterogeneous reaction. So, let us now go into the first step of adsorption. So, let us look into the, let us go a little bit deeper into the adsorption process. So, toluene in the gas phase, it gets adsorbed onto the vacant site S on the catalyst and leading to the Ts, which is the site which is adsorbed with toluene, and Ka and K minus A are the corresponding specific constants. As toluene adsorbs to the catalyst site and the catalyst and the adsorbed species reacts with hydrogen in gas phase, we assume a single site mechanism. So, the rate of adsorption can now be written as Ka multiplied by the concentration of the vacant site Cv multiplied by the partial pressure of toluene. That basically captures the rate at which the forward reaction is going to happen in order for toluene from the gas phase to get adsorbed onto the catalyst site, minus the concentration of the, or the number of concentration of the sites in which the toluene is already adsorbed, divided by the corresponding adsorption equilibrium constant. Okay. So, Ka is the specific constant, adsorption rate, adsorption constant, and Cv stands for concentration of the vacant site on the catalyst, and Pt is the partial pressure of toluene. Pt is the partial pressure of toluene, and then Cts is the occupied site concentration. Cts is the occupied site concentration, and Kt is the adsorption equilibrium constant, and that is typically given by Ka divided by K minus A. So, that sort of captures the rate at which the toluene in the gas phase gets adsorbed onto the catalyst site. Okay. So, let us take a look at the, let us go into the details of the next step that we outlined, that is the surface reaction part. So, let us look at the surface reaction. Let us look at the surface reaction. So, let us assume that it is a single site reaction, where only toluene molecule which is adsorbed onto one site is what is involved in the reaction, in the catalytic reaction. And so, we have hydrogen which is in the gas phase plus the toluene which is now adsorbed onto the surface, reacts with each other, and then it leads to the formation of benzene and the methane in the gas phase. Okay. So, now we can now capture the rate at which this particular reaction occurs. So, the surface reaction rate is now given by Ks multiplied by partial pressure of hydrogen into the concentration of the sites in which the toluene is actually adsorbed minus the concentration of the number of sites concentration of the sites in which the benzene is adsorbed, which is a product multiplied by the partial pressure of methane divided by Ks. So, the first term here corresponds to the rate of the forward reaction, and the second term here corresponds to the rate of the reverse reaction. So, here Ks is basically the specific constant for forward reaction, and pH2 corresponds to the partial pressure of hydrogen in the gas phase, and Cts corresponds to the concentration of toluene, number of sites in which the toluene is adsorbed, and Cbs corresponds to the concentration of the number of sites in which benzene is adsorbed, the product benzene is adsorbed, and Pm corresponds to the partial pressure of methane in the gas phase, and Ks is basically the corresponding equilibrium constant, which is given by Ks divided by K minus S. Okay. So, next we look at the desorption process. So, that is the third step, which is the desorption process. Now, here the benzene which is adsorbed onto the surface gets desorbed to give benzene in the gas phase and an empty site or a vacant site, and so if the corresponding specific constants, desorption constants, are Kb and K minus B, then the rate can be written as rate of desorption is given by Kb into Cb dot S minus Kb into Pb into Cb, okay, where the Kb corresponds to the benzene adsorption equilibrium constant, and Cv corresponds to the concentration of the vacant site. Remember that the reverse reaction is basically where the benzene in the gas phase can actually go and adsorb onto the vacant catalyst site, and therefore, Kb Pb into Cv tells you what is the rate at which the free benzene which is available in the gas phase gets adsorbed onto the catalyst surface.